Not alchemy. All right. So here we go. All right. Got a laser pointer. Okay. When I hit this mirror, I want you to point where you think the reflection is going to go. Ready? See it? Everybody good? Okay. Now, if I go right here, where's it going to go? Did I get it? Did you get it? Okay. So this is demonstrating the law of reflection. It's pretty intuitive. Um, so, law of reflection. The angle in is equal to the angle out. More specifically, the angle of incidence is equal to the angle of reflection. Angle of incidence is equal to the angle of reflection. Okay. A subtle but important detail when we're dealing with optics, with light stuff, the angle that we measure from is from the normal line. You remember normal force last semester? Okay, is always perpendicular to the surface. The normal line also is perpendicular to the surface. So we don't measure this angle, we measure that angle. Okay, with light. Just how we do it. Okay? So angle in is equal to angle out. Okay? Now, if I have this, in order for you to see things that aren't a source of light, it's from reflection. Okay? Can you see this laser pointer on the ceiling? I can too. How is it that everybody in the room can see this laser dot? It's reflecting off of the ceiling into our eyes, but like it's reflecting into your eyes and my eyes and everybody else's eyes at the same time. Did we just break the law of reflection? Seems like a really lame law if we could just break it that easy. The reality is it's a diffused reflection, meaning that the surface that we're hitting is rough comparatively. So when it hits, it obeys the law of reflection at every interaction, but it's not perfectly smooth. Okay? It's like all haphazard, so it's going all over the place.
So you're telling me if the ceiling was completely flat, we wouldn't see it?
Correct. Gabe, is that what you're going to ask?
Yeah.
Okay. So here, watch. You see it. It's pretty bright on here, and then when I hit the mirror, just see how it gets a lot dimmer? Because most of it is being reflected. There is some, the mirror is not perfectly smooth. There is some diffusion. And that's why you can see it.
Isn't the board just as smooth as
Oh no, not at a microscopic level. Cool with that?
Okay, so if you got like a dull
something that's not like glass or silver at all, like
Yep.
dark brown rock, and it's completely smooth. Same as a mirror.
So the thing that makes something shiny is at the molecular level, it will cause those light rays to bounce off. So the fact that it's dull. So if you've ever painted like a room, you have different sheens. You have like flat and semi-gloss and gloss, like high gloss. Okay, the dull is um, more forgiving when you paint, but if you ever get dirt on it, it's harder to clean off because there's like divots and stuff, and so when the dirt gets in there, it stays in there. Versus um, high gloss, it's less forgiving. Like you can see all your mistakes and brush strokes, but it's easier to clean. So like suggestion when you go to paint, when you have your house, painting bathrooms and kitchens, doing like at least a semi gloss beneficial because you can wipe stuff down easier. Does that make sense? Okay. So not smooth from our point of view. Not like, oh, that's so smooth. It's like smooth from a reflective point of view. Okay. All right. So to see things, your eye is the receiver, not the emitter of light, is the catcher.
I have a question.
Yep.
Is there anything that actually exists that's perfectly smooth?
Nope. I mean, you get them like some of the mirrors that they use on the James Webb Telescope spent lots of money to manufacture something really smooth. I mean, it's really close to perfect, but perfect is pretty unattainable. Okay. So, in order for light to get into your eye, it's going to bounce off this mirror and go into your eye, obeying the law of reflection. Right? So, again, light's not going out of your eye. You're not shooting laser beams. You are catching the light. So, you see the object right here. Does that make sense? So this is, so if you've ever seen like a baby or a dog or a cat play with their reflection in the mirror, they see this other thing a certain distance away, depending on how far they are away. So you're like your object distance is going to be equal to your image distance. Good with that? Okay. Just give you a heads up on these problems. There's geometry. Think triangles. It's not hard geometry, but it is geometry. All right. So object distance equals image distance. All right. So if you you gotta coach me on this one. I don't want to videotape everybody doing this, but can you see yourself like a good height? Yes? No?
Yeah.
Is that yes?
That's too high.
Right there? You guys are way better in first hour. First hour is just like I'm like, talk to me like I can't see myself like I know. Tell me. Yes? Good height? Okay. Ashley, can you see yourself? Can you see Jacob? Oh.
I was able to. I was
Yeah, Jacob, can you see yourself?
able to.
Can you see Ashley? Okay. So if you can see somebody in the mirror, they can see you. Okay. So um, if you've ever like been passing a semi, some of them have on their cab, make sure you can see my face in the mirror. Because if you can see them, that means they can see you. And you don't want to be in their blind spot. That makes sense? Okay. So, um, oops, hold on a second. I'll give you a chance to. Right there. Take one, pass one. E4. Okay. So with a plane mirror, so these are known as plane mirrors, like two-dimensional plane type geometry plane, not airplane or like vanilla plane, but like okay. So on the front of ambulances, they write ambulance like this. Why would they do that? So when you're driving and you look in your rearview mirror, you're like, oh, there's an ambulance coming upon me. Okay, you can try it by like facing that way and sticking your mirror like that. Get that? Okay. So, if you buddy up with somebody, you can do some cool tricks with two mirrors. Um, you can like see forever. You guys know what I'm talking about? Like look down a hallway of mirrors. Okay. If you put them at a right angle to each other, that's always fun. Sorry, took your self-portrait in the video. My bad. Okay. With two mirrors, you could build a periscope. Like in the submarines, they're like periscope up. It's the thing where you can look over stuff. So how would you arrange your mirrors to do a periscope? You need a partner.
Thank you. She's smiling. See if I can see Sam. I see
Oh my
Sam.
gosh.
Sam? Sam.
See, I'm orienting to that.
I can see Sebastian.
Mr. Smiley, if you look in my mirror.
Yep. Nope, not like that. There. Wait a minute.
Oh, your face is so funny.
There's look at that.
Can I borrow these mirrors on a test? So I can just like look, so I can just like look over here. Like,
Very sound.
dude,
That would
So-
be.
dude, that'd be so easy. I'd be like, I just like hold it over here. You know?
Yeah, it won't be obvious.
It won't be obvious.
Not only is that unwise, that's also like unethical. You know,
I'm using physics.
to cheat. Yeah. Injustice doesn't justify the means. All right. Good to that. Right and left inversion. Okay. Question. What is the minimum length of a mirror that you need to see your whole body? Like you have a mirror hanging up on the wall, like one of these things, and you want to see your whole outfit, top of your head to the bottom of your shoes. I want to like how long? Hmm.
I'm trying to think of a mirror that Oh, wait, that's actually no. Oh, but also there's some things that. Yeah.
Because we can set this up.
Yeah, like if you just stand back.
Okay.
I just studied mirrors like no matter how far I stand.
Anybody want to try this out?
That's like the
Come on. Okay. I need somebody else to help out with this one too, because awesome. Thank you, Sebastian. All right. So, so what I'm gonna do, actually, Sebastian, you hold this, 'cause it's gonna be hard to coach that. Hold it up and try to hold it vertically. Okay, go up. Can you see the top of your head?
Yeah, oh, I see everything.
Okay.
Should I go like closer or what?
No, stay right there. Hold on. Okay.
I'm putting it on today.
So, you tell me when your feet disappear.
There you go.
Okay, come
They're going.
come close. Oh no, sorry, Sebastian, you just stay put.
Did we mess it up?
So you move close.
Well, I see my feet now.
Yeah.
Oh, wait, what?
Yep. Still see your feet?
Yeah.
Okay, so
Now my head's going.
how's that?
I see like a little bit more.
Okay, here's the deal. Half your height.
Half?
From here to here. Half your height. Does not matter. Thank you, gentlemen. Appreciate it.
Yeah.
Does not matter how far or close you are away. Which is wacky. Okay. Okay, so here's you looking. Here's the mirror that's hanging on the back of your door or wherever you put your mirror. Okay. In order for you to see you need light to reflect to your eyes. So light's coming off of your toe, obeying the law of reflection and going into your eyes.
That makes sense.
You don't need all of that.
What?
To see the top of your head, you just go from. Does that make sense? So you don't need that part. Just this part here. And it does not matter how close or far. We'll go close because most people don't believe the close. Obeying the law of reflection. Okay. To prove it, take the mirror that I gave you and close one eye. Look at your reflection. Hold the mirror close and see how much of your face you can see in the mirror. Okay, like from ear to ear, from ear to eyebrow, depending. Like, okay, everybody got figure out where they're at. Now go at an arm's length and see how much more or less you can see of your face.
Wait, can I test something else?
Maybe. Okay, it doesn't matter how far away or close you are. It's the same amount of face that you can see in the mirror. Okay, that's if you're looking at yourself. That only works for looking at yourself. If you look at stuff like in the background, I can see half of the room doing this, where the mirror's close to me. But if I hold it out like that, all I can get is Aiden and Finn. Okay? Does that make sense? So that's where we get this idea of like it depends on how far away you are. You're looking not at yourself, but at the background. Good with that? Okay. If you could pass those mirrors back up. Cray, you're doing all right there, dude.
I stayed up way too late last night.
Yeah. Thank you. Pass those up, please.
Yeah, I think that like, just like my mirror is like halfway or whatever. When I'm close, I can't see anything. When I'm far away, I have to be like at the back of my mirror to see. Like, why is it?
It could be angled, like it might not be.
I have it like rigid to
Is it one of those mirrors?
kind of, yeah.
It's a flat mirror.
Yeah.
So when you're close, you can see what?
When I'm close, I can see like the top half of my body, but I have to like stand at the back of my room to see my feet.
My guess is it's angled slightly. Like the wall might not be perfectly vertical. Does that make sense?
Yeah.
Thank you. All right. Now, this like one way or like two way, like one side looks like a mirror, one side looks like a window. These surfaces are semi-reflective, semi-transparent, and you can sort of see through, sort of reflect. The who experiences the mirror side is always sitting in the brighter of the two places. So these people at the conference table is going to see this as a mirror. The people spying on them see this as a window. If you were to turn on the lights in here and turn off the lights in there, the conference room people could see these people, and these guys would see this as a mirror.
Wait a minute, you mean to tell me two-way rooms are fake? Like two-way mirrors are fake? Like it's not really anything to do with the mirror, it's just the lighting?
It does have to do with the mirror. It has to be semi-reflective, semi-transparent. Like this doesn't work with windows, but It sort of kind of does. I mean, think about when you're at night, your windows, if you have lights on in the room, it's hard to see out because of the reflection, like the glare. But if you're on the outside in the dark looking in, everybody can see into your house. That makes sense? Okay. So, yeah. All right. Next up are spherical mirrors. These are curved mirrors. They're part of a sphere. Concave mirrors, you're going into a cave. Convex is like you're flexing, so you get a bulge. Okay, that's how I remember the terminology there. Good with that? Okay, so a concave mirror, when the lights go in, rays of light go in, they bounce to a focal point. If you've ever made like a solar cooker, this is where you put your marshmallows, your hot dogs, or okay, bouncing rays of light in. Okay. This is how radar dishes are designed. So rays go in here, they bounce to this focal point. Okay. That's a dumb. All right, so okay, so concave. So you're looking at the cave part. Okay, hold your mirror out at a far, like arm's length away, and look at yourself. Okay, how would you describe your image? You think? Ah, are we serious? Okay, real quick. Go arm's length, then go close. Go close. You should be able to see your eyeball real big. Okay? Okay? And now go look at convex and look at it. It doesn't matter. That was the bell. Goodness gracious.